Okay, it's now time to learn how to solve problems with the Schrodinger equation, at least non-trivial problems. And the first one that's usually dealt with, because it's very instructive and not too complicated, is the infinite square well, it's called. We'll introduce the actual potential function in a minute, but first let's review the conditions we developed in the last lecture for the wave function. It's continuous, its derivatives is continuous, or sorry, yeah, derivative is continuous. It has to die off as we go to infinity, and it's normalized. Now, the plan of attack is as follows. So here's what we're going to find. We're going to create a graph of the potential versus position, and then break the problem into parts, piecewise as we can. Then for each region with the same value of the potential, because potential is going to be constant in this case in the different regions, we write out the Schrodinger equation. And then for each region, we go down and rewrite the general form of the solutions in those three regions. And then we proceed through the conditions above, and we're not going to go in order of them because it's not advantageous, but we first employ condition 3, that any terms that blow up as you go off to plus or minus infinity, we drop. That's what that condition 3 imposes. Condition 1 says we match wave functions when two regions meet. We call that satisfying boundary conditions, and that's where the real interesting part lies. Condition 2, match the derivative of the wave functions at boundaries. In this particular case, it turns out we won't use condition 2. In others, you will. And lastly, condition 4 would normalize the overall solution. And we won't worry about normalization in this lecture. There's enough to do here. And lastly, we should include the time-dependent portion, tack that on at the end. And then again, those last two parts we'll not do in this particular lecture, but we'll leave that, well, normalization will be left as an exercise. So let's, first of all, so what we need to do is find the general forms here if the potential is constant. So if the potential is constant in a particular region, there's three possible scenarios. The potential is 0, the energy of the particle is greater than the potential, or the energy is less than the potential. Those are the three possibilities. So let's go through those in turn. The easiest is v is equal to 0. The Schrodinger equation takes this form. Now, what we're going to do is rewrite this in a way that makes it easier to see or to solve the differential equation, second order. So we're just going to multiply through by minus 2m over h bar squared. And then we can isolate the derivative on the left-hand side. And we get this constant here times psi. And we see this is a very simple differential equation. And we're going to identify this, this term here, 2me over h bar squared. We're going to call it k squared. And there's a reason for that. Makes things simple. But the point is here, we can solve this simple differential equation. The second derivative of psi is equal to minus k squared psi. It's very easy to solve because the minus sign says we need an I in there because we're taking two derivatives and we're squaring the coefficient. So that means we can write the solution in this form as a e to the ikx plus b e to the minus ikx. We need to include both of those to be general. So we can't just use one e to the ikx or e to the minus ikx. This is the full general form. Using the Euler relation, we can also write this as sines and cosines. C cosine kx plus d sine kx. And again, k here, going back, is square root of 2me over h bar squared. Okay. Now, in the condition that e is greater than the potential, again, we rewrite the Schrodinger equation and in this method. Again, the coefficient there, 2mv minus e, I put absolute value signs there because e is greater than v in this particular case, so k is still a real number here. And so we can write this again as minus k squared psi. This is, again, is minus, it's the same form as above. I should probably call it a different constant, not k again, but that's okay. This will be understood as we go along. But again, we get the same type of solutions, either complex exponentials or sines and cosines. And whichever you use, you can choose whichever depending on the context and whichever is easier. And here this is k takes out 2m e minus v over h bar squared. Lastly, we want to consider if the energy is less than the potential. Now this is something that's different that you don't experience in classical scenarios. But here we can solve the differential equation. Again, now we have a plus 2mv minus e there. And we're going to call that kappa squared. Now there's a positive sign there. And since there's a positive sign there, now we have the wave function solution takes a form of just real exponentials or exponentials with real exponents. E to the plus kappa x plus b to the minus kappa x. And again, that's the full general solution. And again, kappa is equal to 2mv minus e, where we just flip that so we can make kappa real. All right. So what do we do? Well, let's draw this. Now we're going to draw the region here. So I'm going to hand draw this. So I'm going to make a graph here of, let's go like this, of x versus potential. So I'm going to have, let's go here. So this will be x equal to 0. This will be x equal to L. So I'll go ahead and write that in. So this will be 0, L, and this is x. Now the potential, I'll see if I can write that in a different color. Let's see if I put it in red. Again, is easy to write in, well, in here, it's v is equal to infinity. And in the middle it's 0, and on the other side it's, so 0. So red will indicate potential, like this. I'll just do it that way. And those are my regions. And now I'll go back and, now what we want to do is split this up. This is what we said. So we clearly have 3 regions here, and I'm going to label them 1, 2, using Roman numerals here, and 3. So we have 3 different regions here, and we'll go through in turn. And I'm going to do this, kind of do steps B and C together, and we'll write out, I'm not going to bother to write out the Schrodinger equation. I'm just going to go straight to the solutions. But clearly in regions 1 and 3, the energy is less than the potential because the potential is infinite, clearly. And in region 2, clearly the energy is going to be greater than, or because the potential is 0, we always saw the type of solutions. So going back to the general type of solutions we discussed before, just quickly look here. Oh, okay, that didn't work. Here. We have that in region 1 we have real exponentials, or exponentials with real coefficients. That's what I mean by that. For region 2, we're going to use sines and cosines. That turns out to be easier in this case to employ. And then for region 3, we have the general solution of exponentials again. Now again, I'm labeling all the coefficients and all the k's with their subscript, the region that they belong to. Now employ condition 3. So condition 3 now says that as we go off to plus infinity over here, the wave function has to die off, and over to minus infinity has to die off. So this only applies to regions 1 and 3. Region 2 doesn't contain any infinite parts, so we don't worry about that. And we can see right off the bat what's going to happen here. Again, so we're just considering 1 and 2. So in region 1 here, the x is negative. So that means if we put in a negative x here, this exponential becomes, whoops, that's not what I wanted to do. This exponential becomes minus infinity. If we put x equal to minus infinity in there. And this one becomes x plus e to the plus infinity. So this one is a problematic one because that's going to be infinite. This one dies off because e to the minus infinity is 0. And again, because we're saying because kappa, remember, is proportional to v, the square root of v, and we stick in a infinity in there, it's kappa is infinite in this case. And in region 3, we have x is positive, so this one is going to be the problematic one. That's going to be e to the infinity, and this one's going to be e to the minus infinity, which is 0, so we don't worry about that. So let's do that, and I'm going to erase my, why did that go away? I'm going to erase the drawings. I think I'm going to erase the drawings. And what we see is that we have these conditions. Condition 3 is going to say that the, well, hold on a second. There we go. Sorry. Okay, so condition 3 says that, well, at these we get e to the bi to the plus infinity. And again, like I said, e to the a. So what condition 3 says is that b1 and a3 have to be 0. So condition 3 allows us to set them to 0. But what that does, it just says that in regions 1 and 3, because well, we just get that size equal to 0. And that should be expected because we have an infinite potential. We should have 0 probability then that the object's in region 1 and 3. Now we come to the important part is we go to region 2, and now we are done with condition 3. We go to condition 1, sorry, in region 2, we make sure that the wave function vanishes at the boundaries, x equal to 0 and x equal to L. Satisfy boundary conditions, we call that. So let's look at that. So here, here's our general solution again. And let's look at condition 1 at the x equal to 0 boundary, and this we call this boundary conditions, or BC for short. So here we said that, well, in region 1 it's 0. In region 2 we put in x equal to 0, and we get a2 cosine 0 plus b2 sine 0. Sine 0 is 0, so, and cosine 0 is 1. We just get that a2. And a2 then is equal to 0. So this condition, boundary condition, says we get rid of the cosine solution as a possibility. And that makes sense, because if you want it to vanish at the boundary, cosine is 1 at the boundary. We can't do that unless a2 is equal to 0. So that reduces our solution now to only the sine term. Now we go to the second boundary at x equal to L. And so this just says that psi 2 of L is equal to psi 3 of L at that boundary. And it's equal to 0 because psi 3 is 0 all over the place. So we have this condition that B2 sine K2L is equal to 0. Now how do you solve that? Well, there are trivial solutions. If you say that B is equal to 0, okay, that will solve it. Or you could say that K2 is equal to 0. That also solves it. But those are trivial solutions because of the fact that because in that the wave function vanishes everywhere. That means we're not even talking about a particle being anywhere anymore. So that's what here we have. So they're not they don't even contain a particle. So what we must have is that the sine KL term must be equal to 0, and the only way to do that is that the argument there, KL, must be equal to an integer value of pi, because we know that the sine n pi is equal to 0, and n is an integer. We start from 1 because we don't want to consider the trivial solution. So n is equal to 1, 2, 3. So this condition here satisfies, and what it does is it pins down the wave function at the two boundaries, so that we get only discrete solutions that are allowed here. Now we can solve this going back to the form of k, which was the square root of 2me over h bar squared, times L is equal to m pi. Let's solve that for the energy. And what we get is the allowed energies for the particle in the infinite square well. This is really the key thing we're interested in, that the object cannot exist in any energy state within the infinite square well. It can only exist in these discrete energy values. This is new. This is unlike classical physics. This is how we get to quantized energy values, and it's sort of the word that we use for quantum mechanics. Okay, so let's again look at our solution again overall. Let's just summarize here. So we have that our solution is psi is equal to b sine nx between 0 and L and vanishes outside. The allowed energies are e to the n squared pi squared h bar over 2ml squared. And the last thing we do is normalize, which we'll leave as an exercise, and tack on the time-dependent part, the e to the minus I et over h bar portion. Let me just quickly sketch what the solutions look like. You've probably seen this before, hopefully. But the first one, which we call the ground state, looks like this. So if we just look at it, it's going to fluctuate in time, but that's what the amplitude looks like. Secondly, we can go like this. This is the n equal 2 case, which is just looks like a sine wave. That's just sine x, and so on. And so we get to the higher energy states. We're going to get more nodes like that, and so on. And there will be an infinite spectrum of these, but it's a discrete infinite spectrum. Okay, that's enough for now. We'll look at more complex scenarios here, but you should review this and make sure you're thoroughly familiar and comfortable with this solution. It is actually the most basic quantum one to solve.